everyone. Thanks for joining my talk today and skipping the other one, which is on infinity, and this one is more on power. So you chose power over infinity, which is cool. So yeah, last year I went over the control over time limit. I lost control. Which was like 14 minutes or something, but this year I'll try to, keep the control on time. So energy implications of your Go code. Why would you care about energy? When do you care about energy? Any answers? Anybody here cares about energy of their code? Why is it important? Is there any? By any chance, do you work in robotics? Or it's like, okay, so well, cloud providers care a lot because they want to run the application, of course, fast and also consume less as possible because it just directly affects their bills, electricity bills, obviously. And so, but the reason I care about energy is because I'm active in robotics and AI industry now. And that's why most of the robots that are on limited energy budget, they're, are supposed to be wise with respect to the energy they're consuming. Sorry about the sidebar, by the way. So so performance has been a first-class concern in this community. Of course, there are many toolings developed for it, and Go is perfect with performance, obviously. With the lightweight gophers, the Go routines, clever scheduling policies, and byte-level access, memory accesses, concurrent memory models, and et cetera, makes Go best candidate for performance optimizations and gives good control to the developer to control performance, of course. Of course, performance together with productivity and scalability are the other major concerns of this community. We've seen that when benchmarking Go against other programming languages like Python, of course, in many applications, including the AI ones, performance over 100x sometimes. And it's a useful and it's important for us to adapt this language across company and use it for to get good performance, run the code faster, and meanwhile save a lot of energy, of course. I don't know if you've come across this article, which is there are a couple of performance tips. The author, Valentin de Laplace, if I'm not wrong, proposes that by just implementing, considering these optimizations, the author achieves 23x performance, not by replacing the hardware, not by spending money on different accelerator or anything else, but just considering a set of high-level rewrites, refactoring code, achieves good performance, 23x. And that's on a business use case for airline control and use case like that. So what I thought was, okay, these are performance tips, it's very interesting, and bear in mind when implementing an application for performance to gain best performance. But on the other hand, I was thinking, okay, is there possible to come up with a power, tips, a set of power tips for energy so that it could be used as a guideline for our engineers in the company and say, okay, these are basically the kind of refactors that you have to consider for minimizing energy consumption of the applications when, well, they're deployed on robots that are using, they have limited battery budget, basically. So yeah, that was the idea to come up with something, set of guidelines, basically. So the other dimension, beside well, performance, is energy and power that I'm going to talk about and mention why we care a lot about energy in the company and a little bit about the company itself as well. This is research recently published by a friend of mine, Amrali from Carnegie Mellon. It's a Safari group. They've made a couple of observations on applications running on edge devices, really. And the first one, which is very interesting, is like almost like two-thirds of energy consumed in edge devices is, is due to data movement. And the second one is a significant fraction of data movement often comes from simple functions. And what they're proposing, actually, is a new architecture, is a new hardware system that is actually probably, well, together with Micron Systems, and they're working on moving computations, like the CPUs, into memory substrate, and moving computation inside memory so that the travel, not only bandwidth increases, but also the time that data moves from memory to computation also, shortens and save a lot of energy that way. And well, obviously this is an expensive solution, and hopefully it's going to come in the next few years. But this is something that I thought, okay, not everybody has access to these machines, and they're going to be expensive. So why not looking at cheaper solutions, being more aware when coding stuff, and taking care of energy at higher abstraction levels. But yeah, I think the industry moving toward implementing and looking at this kind of architectures where computation sits in memory. That way they decrease the data travel movement across the system. So a little bit about the company, and what we do is most of the AI models that we have, they're deployed on either they're stationary, that they are on our servers for post-processing and stuff, but also the AI models for like visibility and vision and post-processing, camera data and sensor LiDAR and technologies like data like that. We use AI models that are deployed on robots, and so 2 gigabytes per second data generated like on site from different deployment sites. They are coming in for inspection, and customers expect digested detection data as output and report from us, basically from the company. So one of the models we recently were looking at was the robots are working in a harsh environments or foggy, rainy. These are the robots that are like the models that enable these robots to be able to detect objects in these environments is, and also kind of, which is the technology is called SLIM, is recently came out, and there's a lot of research work going on this bit. And it's kind of models that, like these are AI models that are efficiently designed, and they are, running on either on stationary servers or on robots to enable them to see through haze, fog, and all that. I don't know if you've heard about convolutional networks, graph convolutional networks, but you don't really need to know much about this for the rest of this talk. But these are the kind of graphs that we're dealing with and we're working with. They are convolutional networks, and it's not just one; it's just handful of them that communicate, and this is the way our graphs are built. Computing like different subsets of these graphs, different in some cases we need subset of these graphs to sit on robots, for example, for vision purposes or for audiometry and technologies like that. So the reason, now I'm picking a use case here that is the graph systems, and the graph systems for processing graph systems. There were other use cases that I could look at, like Docker or technologies like this. But at this point, yeah, graphs are important to us, and it's the reason we are choosing this use case. How many of you know about this system, the Pregel? Have you heard of it, like the Pregel system? It came out of, it's by implementation by Google. It's almost same idea, same time as CSP came out, which is the fundamentals for Go, communicating sequential processes. But this model is block synchronous parallel model that it allows, it's Apache Graph, Giraffe, and Graphics. Both are based on this model. It's a distributed computing model, and it's perfect for graph processing and large graph processing. And the reason I've taken this algorithm, this programming model, sorry, is because it gives full control over the number of nodes, the subset of the graph you want to process, and et cetera, et cetera. And the other reason was the Pregel is message passing based, algorithm, and for representing it and coding it in Go, it's much easier to the way you think is like the way you think the vertices talking to each other, sending messages to each other. I felt like, okay, this is very easy to implement and realize in Go, and then look at improving its performance by removing all those channel-based communications and making it more efficient. But Go has always been, a go-to language for me. It's like it's for prototyping, it's perfect for me. Like the way I think, it's easy to represent whatever I think and code it as quickly as possible in Go. There is different implementations of this Pregel algorithm that I'm going to show next. Well, this is a Pregel programming model that I've coded PageRank algorithm in 3 different forms. So it's like one of them is matrix-based, and the other one is Pregel and using Pregel, which is basically considering supersteps and considers a graph with vertices, expounds a Go routine, the Pregel implementation actually, expounds a Go routine per vertex, which is not efficient, obviously, and considers and these nodes communicate to each other through channels and talk to each other through channels and pass updated data to the neighboring nodes and update their own values by receiving messages from the neighboring nodes. There is a stream version. I call it stream, but it's sequential. I've got rid of the Go keyword to make it sequential rather than spawning one Go routine per vertex. It's like basically there. For this experimentation, I could have consider different subsets of the graph regionized or graphs decomposed into subsets of vertices and all that, which is the next step, the next flavors of implementation, basically. But yeah, for now, so okay, we have 3 different implementations. One is matrix-based, Pregel, embarrassingly parallel, and one sequential one. So to get some idea of if I could use Go tooling to understand what's really happening, and if I could just, which of the implementations is more energy friendly, let's say, and so for power measurements, I'm using PowerStat. It's and the guidelines for benchmarking is from the Corey from GopherCon guides. They did the workshop yesterday, actually, on advanced workshop. They talked interesting tips on benchmarking and technologies like this. So for measuring power, what I considered was to isolate the system, make sure no other programs are running on it, and just using PowerStat. Also, PowerStat requires you unplugging the charger, because it has to make sure that the device is discharging. It relies on RAPL interface provided by Intel, well, on Intel processors, of course. I'm going to look at ARM-based libraries as well at some point, but this is mostly Intel interface for uses energy counters in each core, and does the measurement that way. So yeah, a couple of interesting tips for benchmarking your. It's general enough. It doesn't need to be for. It's not just for this use, this practice, but also for as general tips for benchmarking your applications in Go as well. For the cases when we had sparse graphs, like the connectivity degree of 2, let's say, with thousands of nodes, and stabilize that for T steps. The Go tooling, which I'm using Go test bench for and bench mem, it gives me what we can see from the numbers here is stream which is a sequential one, doing much better in terms of performance compared to the matrix implementation and Pregel implementation. And as I'm increasing the degree of connectivity in the graph, the matrix one, which is has static allocations in the start from the beginning, it's not much different, but Pregel gets worse. Stream, the sequential one still remains the same, but for this kind of graph processing, basically what the message here is that, well, usually we consider matrix-based operations, but sparsity and graph sparsity is a factor here that is affecting the performance and memory allocations, etc. So from what you see here is that matrix is not a good option for this kind of applications, for instance. PowerStat gives me the power numbers and the clock frequency of the processor as well. So starting from 5 watts to it jumps to 12 and remains at 12. I mean, it goes up until 14, 16, and then comes down. This is for matrix. As I said, I used this command for measuring power. And well, obviously, okay, PowerStat is not Go tool. At some point we were thinking, okay, it would be nice to have this in Go tooling as well, like something that could do like Go test dash energy, for example, and measure performance that way. So I'm running out of time now, but yeah, I'll just. There's another implementation which is the Pregel. Pregel is you don't see much. This is just power numbers, but I'm gonna show you like the behavior of the application as well at some point. Yeah, as I was saying, like power stat is not included in Go machinery, but we submitted a proposal saying that okay, this would be nice to have it, to have like whenever I code something, the 2-3 different applications of in different forms. Trying Go test dash run energy to give us some some notion of energy and what's going on in the application basically. The stream, which is a sequential one and running on a single core, is basically output from the others in terms of power, and in terms of energy. Data movement across the cores is something that I would like to know more about. Go tooling doesn't give me much about. Like I'm using trace tooling here that is initially was designed for Chrome, but now it's for measuring performance of Chrome. But it's now repurposed and is used in Go. As part of Go tooling, basically. But the perfect thing would be to understand like how much of data objects are moving around across the system, across cores, which is not really. But from this trace tooling, what it gives me some idea of the heap allocations, heap utilization, and the number of threads allocated per segment of time on these 4 cores that are my machine now. And so as you see, heap allocation since the beginning, it remains same, and then there are functions that are keep fetching data in, processing, and putting back. And there's as you see, there's a lot of, it's understandable to see why, in terms of energy, this matrix implementation is not doing that well. When it comes to the other one, which is the Pregel one, is we see a lot of communication between the cores, and communication between cores, and but heap size is not as bad as the matrix implementation. Why? Because first of all, regarding the implementation, each of these gophers gets Go routines gets their own set of input array, input edges and output edges, and basically they are in their own scope. It could use as stack objects, not much to do with the heap. So obviously, is another observation here that utilizing stack is cheaper than heap in terms of power. And when it comes to the sequential one, which is the stream, the communication between the cores, it's not communication, but it's because it's running in test suite. There is the test runner, and then there's garbage collectors that are allocated to other cores that they're taking care of the garbage in memory, and thread utilization. This one is doing much wiser, and it's understandable from how it affects the memory, but similar behavior with the heap. This was what is obvious from these experimentations. A couple of tips, power tips, as I said, was the initial idea of coming up with some guidelines and ideas that how high-level coding and being aware, energy aware, programming can affect your energy consumption of your system. on your application, sorry. So one of them is the sequential implementation versus concurrent one. I don't know if you notice the clock frequency of. So the clock frequency is like it goes up to 3 gigahertz at some point. It's increased while this is the scheduler that is trying to get this job as quick as possible done. But this doesn't much happen with Pregel. Like it's close to 3, but it's not as high as, because there's no necessity for it. Here, so this scheduler does a lot of calculations, of course, behind the scenes, but sequential implementation may perform the concurrent implementation depending on the application. And obviously, this is a energy tip if you don't care much about the performance, but these are correlated, obviously. Like if your program runs fast and finishes job quickly, its power consumption is going to be lower, but obviously, well, these are is also the matter that how much energy per these time slots are spent. It could be like running a core for a few seconds, like say 10 seconds at 2 gigahertz versus running it like 5 seconds and at 3 gigahertz. Well, these are different power profiles, of course. Many simple customized operations outperform few complex operations. So the simple customized operations, I mean, in the Pregel form for PageRank, each one of these nodes is responsible for just a very simplistic computation. It just receives the messages from the input edges and does a multiplication and spits it out to the neighborhood cores, vertices. There's many of them that's happening per core, but versus matrix multiplication, which has eigen value computation and matrix inverse computation. These are different, obviously, behaviors here. Memory locality is important, like CPU cache friendliness, like how much data, like is similar to the idea of like minimizing the data movement across the system. Amount of data objects moved around in the system is like stack-based implementation less than heap-based implementation, which is, yeah, as I said, like a Pregel implementation has its own variables, has its own arrays per struct, and then it could utilize the stack much better than the way the matrix implementation is doing, which is from the start is allocating large chunks in a heap and brings data objects in and out, and this is not energy friendly. The other point is fine-tune scheduler that, well, if it's fine-tuned for performance, obviously, it's not going to care much about like data movement in the system. It's going to be the main purpose is utilize CPUs as much as you can, keep them all the time busy. But but scheduling with respect to performance, well, it's a different policy. Like if there's like data has to move from core A to core B, and if you're dealing with a 16-core system, and the data travel time and all that has to be taken into account when considering scheduling has to be restricted with respect to the application you have. Minimizing data movement, like probably it's a better idea that data remains on the core 1 and wait for the previous task to finish, than assigning the go routine to another core, basically to get the job done as fast as possible. So it's a different scheduling idea, of course, and different policy. So other activities we go related to Go in the company. There's one which is GoBot, which is entirely the framework written in Go, and there's a ROS-based implementation of which is Go that we're using for data collection, making sure the services on the robot are active and all responsive, and for taking care of the data in the system, data collection. And well, there's a Go counterpart of this framework. And some of our, most of our, Python code bases in Python and C++. What we were looking at was this tool called Grumpy that does a static linking of the Python to uses Go libraries already compiled and then replaces the Python functions with those and makes it easy. Is a superset of basically Python. And it allows us to exploit the performance of Go basically at some point and transform from Python domain to Go domain, let's call it this way. But this project is not live anymore, I think, and I haven't seen much activity in this. But yeah, so there's another bit that another activity that we're doing. And yeah, that's all I wanted to talk about today. Thank you so much.